Hello, we are group number 10 and today we will be presenting our assignment on flow in packed beds, correlation and calculation. This topic is a key part of transport phenomena because it combines fluid flow, heat transfer and mass transfer in a single system. We will not just see formulas but also understand their physical meaning and applications. So, now coming on to the topic overview. In this chapter, we will focus on evaluating transfer coefficients. In real systems, fluids rarely flow in empty pipe. Instead, they flow through packed materials like catalyst or absorbents. So we need correlation that can predict pressure drop, heat transfer, and mass transfer. Packed beds make analysis more complex because flow paths are irregular. So let's understand the functions of packed beds. Packed beds are widely used because they provide very high surface area, and we can also here see the diagram of a packed bed. And why is this important? Because all transfer processes happen at interfaces. For example, in gas absorption, gas dissolves into liquid across surface. In catalytic reactors, reaction occurs on catalyst surface. And in deep bed filtration, particles get trapped within pores. So packed beds essentially maximize interaction between phases. That is why industries prefer packed systems over empty pipes.
Now let us understand the flow resistance. In packed beds, fluid does not flow through straight. It moves through tortuous path, creating more resistance. That's why we study friction factor correlations. For friction factor correlation for in packed beds, we use the formula in which contains porosity, particle diameter, pressure drop, length of the column, and the density of the fluid. And it also includes the square of superficial velocity, and the superficial velocity is defined as the velocity when there is no packed material involved in the column. Then deriving the Ergun equation. In Ergun equation, we use the packed bed Reynolds number, which has the definition of simple Reynolds number, which includes the particle diameter, superficial velocity, density of the fluid, and viscosity of the fluid. It also includes an additional factor which accounts for the porosity of the packed bed. And for laminar flow, we have Cauchy-Kármán equation, which has the formula of 150 by packed bed Reynolds number. And this formula is valid for particle Reynolds number less than 10. And the second equation, which is known as Burke-Plummer equation, which is for turbulent flow, has the friction factor value 1.75, and it is valid for packed bed Reynolds number greater than 1000. And the combined equation that we use is known as Ergun equation, which consider both the laminar and turbulent conditions. Now the numerical. The problem is on the annular flow, in which the water flows with a volumetric flow rate of 5 meter cube per minute, and the diameter of inner and outer pipes are 30 and 50 centimeter respectively. We have to calculate the superficial velocity. As per the definition, the diameters we have used in standard SI units, and the superficial velocity comes out to be 25.5 meter per minute, and comparing to the actual velocity, which comes out to be 40 meter per minute. The key observation in this numerical is that the superficial velocity is significantly less than the actual velocity. Then the second numerical, determination of bed porosity, in which we require the given data is the area is 0.8 meter square, height of the column is 30 meter, pressure drop around the column is 3200 pascals, and the particle having the spherical diameter of 6 mm, and the fluid properties like density, viscosity, and mass flow rate is given as follows. The objective of this numerical is to find the porosity of the bed. We use two methods here, first the analytical one and the second the Newton-Raphson method. The analytical solution, for which the step 1 is to calculate the bed superficial velocity, and then substitute in the Ergun equation we get the a cubic equation for the porosity, and for calculating this we use discriminant terms method, for which the m and n comes out to be 0.793 and 0.799. And for then the next step is to calculate the roots s and t, which comes out to be 1.231 and t comes out to be minus 0.644, and the end result comes out to be 0.746. The next numerical, in which we have the given the porosity function, and we have taken the derivative of friction factor with respect to porosity to get the optimum value of the porosity, and for that we use Newton-Raphson method, and it after first iteration the porosity value comes out to be 0.746, and in third iteration it comes out to be 0.745. As we can see that the first iteration and the second iteration, the porosity values are more of similar, so the porosity is around 0.746. Then the next topic is heat transfer correlations, for which we use packed bed Nusselt number, which is a function of packed bed Reynolds number and the Prandtl number. For Nusselt number packed bed, a similar equation is in terms of porosity, overall heat transfer coefficient, and particle diameter is used. The validity range for this equation is given by particle Reynolds number must be in range of 3.7 to 8000. Porosity range is 0.34 to 0.74. Prandtl number is around 0.7, and all these properties are evaluated at an average fluid temperature. Calculation of heat transfer rate. The equation for heat transfer rate is AVV, overall heat transfer coefficient, temperature, log mean temperature difference. For log mean temperature difference, we use the formula of T1 minus T2 upon ln T1 minus T2. And for calculating AV, we have the formula this, which includes porosity and particle diameter. Here is a pictorial diagram for representation. Then the mass transfer correlation. For mass transfer correlation, there is a J factor definition and modified Reynolds number we have to consider, in which the overall mass transfer coefficient, velocity, and Schmidt number comes into picture. Then for packed bed Reynolds number, a similar kind of as we use for normal Reynolds number formula is used. The validity is given by 0.01 to Reynolds number should be between 0.01 to 15,000, both for gas and liquids. And the combined equation is this, in which there is first term which includes the Reynolds number, packed bed Reynolds number to power 0.82, and in second term it includes the packed bed Reynolds number of 0.386. Then the calculation of mass transfer rate. The equation for species A is given by m dot A is equal to AV V, average mass transfer coefficient, log mean concentration difference, and MA, molecular weight of species A. Here is the example which shows the system of naphthalene sublimation.
Now this is a practical industrial example. We have a naphthalene sublimation. Solid naphthalene converts directly into the vapor. Air carries this vapor through packed bed. We want to know how long the bed should be achieve the 25% saturation. This is directly applicable in drying and sublimation process. So this question is having the packed bed with a porosity of 0.45 and the pipe having an internal diameter of the 2.5 centimeter. Then we have the naphthalene spheres of the diameter 5 mm, and then the pure air of the 40 degrees Celsius which flows with the speed of 9 meter per second, and we have to achieve the saturation of 25%. So now we are going to the solution. So now let us understand the derivation. We apply the mole balance here. The rate in is equal to rate out, and we have to substitute the volume in the terms of the length, and then the resulting equation we get this. After rearranging we get an expression. The logarithmic terms appears because of the concentration changes exponentially along the bed. So this equation is derived using the fundamental mass balance principle. So we have the properties and the assumptions where the DAB, NU and the SC is given, and the assumptions we are given the steady state and isothermal and the constant sphere diameter. Now we will calculate all the parameters step by step. First of all, we will calculate the surface area. So the surface area is come up to be 660 meter inverse, and then we will calculate the modified Reynolds number. The Reynolds number of the packed bed, which is come out to be 2655, and then we have to determine the Kc, which is the mass transfer coefficient, using the correlation of the in the terms of the epsilon j mpb, which is come out to be 0.0186, and from that we get the Kc is equal to 0.2 meter per second, and by putting this all values in this equation we get the length which is required to calculate for the 25% saturation, which come out to be 0.2 meter. This is very important conclusion. Packed bed drastically increases transfer efficiency. Without packing we should need much longer length. So packed beds make process compact and efficient.
Thank you. From
Thank you.
number 10.